All right, we're going to start. I've been asked to start everything on time. Otherwise, people in PMAC get mad. My name is Ron Doucette. I'm one of the board members. And today I'm introducing Arun Gowtham. And Arun is the president of the Greater Toronto Area chapter of PMAC. So he's very familiar with this. And I'll leave him introduce the rest of himself. All right. Thank you very much.
Yep. Thank you very much, Ron. Can everyone hear me okay? Yep. Okay, awesome. Very happy to see all the faces on the last afternoon of the last day of the conference. So thank you very much for coming in today. So it means either you really love the conference or dying to hear about this topic. So I'm hoping it's the latter. And I have about 45 minutes session, and I want to share a few things that I've picked up along the way with you all. So I'm a consultant, and in the last couple of years, I've spent a fair amount of time thinking about AI-based predictive maintenance. And I've seen the solutions being implemented, hardware being developed, and the technical challenges have been sorted out. But one thing that I've noticed repeatedly after talking to like a few other clients was that the implementation on the maintenance team side, like how does that particular solution fit into your overall maintenance plan, maintenance work? It takes a little bit of a cultural shift from the maintenance team's perspective, and that's what I'm going to explore a little bit. And the ideas that I'm going to share today are from those, that exploration that I went on to see how can we fit in this square peg into the circular hole. How can we polish it and fit in there? And so that's what I'm going to talk about today. And I know there are a few other topics, a few other presenters on the same topic, but I want to give a little background about myself. To give some credibility on where I am coming from. I've been working as a reliability engineer for the last 10 years. And the seed for that began during my master's degree, where my thesis was on predictive modeling on reliability-centered maintenance. And that's where I initially got interested in using direct analytics for our reliability work. And then over the course of work, I built all those initial IoT hardware devices. Right now, you get all these off-the-shelf, fully packaged devices. And back in 2015, when I initially began, I had to build these part by part from scratch. And that taught me a lot of things about what network to think about, what wireless technology to think about. And then there are a few other fleet management experiences that I got. Like we were monitoring these assets in real time and using it to advise maintenance tasks. And lastly, for the last 2 years, I started my own practice on building machine learning tools specifically for predictive maintenance. I built a SaaS product, and we piloted with a couple of clients there. And what that taught me is also included in this presentation. And so all of this is coming from that experience I'm going to share with you today. And in return for my time, I'm going to ask everyone to just give me a little bit of your book recommendations that you think are very valuable. That's the deal that I'm going to talk today. And a little background about my company too. And now I'm currently part of GHD. GHD is a global engineering consulting firm with a variety of services. We have offices in 14 countries, like close to 11,000 employees. And the great thing about this is we have expertise in a variety of service lines. We have asset management, reliability excellence, asset information systems. That's the CMMS implementation side, and the regenerative assets too. That's our new focus on it. And since joining GHD a few months ago, I've been also enjoying this exploration phase. Like we have a whole digital side, and the asset management group, we are actively pushing with the digital team to see, okay, how can we bring in more digital tools into it? So those kind of R&D projects are very exciting for me. So before I get into the crux of the presentation, I want to also ask you all, just to get like a raise of hands to see, right now, how many of you in your organization have some sort of real-time monitoring, IoT, or any AI-based digital solutions for your asset? 1, 2, 3, 4, 5, 6, 7. Okay, but there is a fair amount of it. That's great. And in your experience, does any of these items that I listed here seem familiar so far? Like, I know the pain that you had to go through in making the business case to put all those implementation plans, to pilot this new hardware and software into this. And you're still facing like few downtimes. There are few failures. And most importantly, the maintenance costs are not coming down. And I've also noticed increasing workload for your team. Like you have all these alerts coming in, you need to manage it, you need to tag it, label it. And that's causing, like, that's pulling resources out of your regular PM work, your regular repair work that you have to do. Does this seem familiar? Yes, no? Okay, and is there anything else that is not listed here that you feel, oh, that's a pain? Or we initially thought going for an AI-based solution will help us, but this is something that we didn't expect. Any unmet expectation? Yes. That's correct. Yeah, the computing cost. Yes, and AWS charges. That's good. We'll talk about that. Yeah. Anything else? Decreased uptime? Okay. Yes. Okay, yes, and those are very good examples. And I want to highlight that all of these are giving a very low ROI on your AI investment. And that's kind of spoils a little bit on, okay, next time when you go and ask for the budget to scale it up. And that also puts a question mark on the technology and adaptability in general. So that's the thing I want to address today. And my objective today is to give you some solutions to get your ROI a little higher. And if you, for some people who did not raise your hands, who are thinking about going into these AI-based solutions, hopefully these points that I'm talking about will give you an awareness of, okay, what are the things that we need to consider before jumping into that. And before we jump in, I want to get everyone on the same page. So I'll quickly go through this definitions because I have my own understanding, and I hope everyone's will follow me when I talk about on the rest of the slides. So we have reactive maintenance and preventive maintenance. Fairly easy, quick. You do maintenance after it fails. You do maintenance on regular schedule. And then we have predictive maintenance here. Equipment is operating, and then you do a prediction ahead, and then you do maintenance before it actually fails. So based on this graphic, I want to define predictive maintenance as it's a maintenance strategy that forecasts an imminent failure with sufficient lead time to take a maintenance action. And all those 4 points that I've highlighted are very important. And that's, I feel, is not fully capturing that leads to some mislabeling and confusion on what is a predictive maintenance. And especially this forecast type. If you are not forecasting a failure, then the maintenance strategy falls into a condition-based maintenance rather than a predictive maintenance. It's the same kind of difference between weather forecast and weather reporting. Yeah, you see weather reporters standing in a hurricane, but no one, that's too late to respond to. So that's the analogy I try to remember. Okay, when you're talking about predictive maintenance, you had a little bit of a forecast, and with the sufficient lead time, we don't know how much lead time, but with a sufficient one. I will dig into the word sufficient in later slides, but that's the definition. And now, since I started this presentation with AI-based predictive maintenance, so what does that definition tell us? I'm going to take the same graphic that I showed previously, but I want to add and say, we're just using some AI tools to do the same work that traditional predictive maintenance does. That's all the definition is. And I want to clarify that because using this tool is just like an aid. You're not changing anything drastically. There's no new types of maintenance process, just same AI-based tools to support your predictive maintenance. And where does that support go into? It goes there. Like when you're making the prediction, you're taking that some support. And that prediction can be in the form of inspection, just normal inspection. That itself is a prediction. And then the standard PDM tools. We do have vibration, motor current analysis, lubrication tomography that everyone is familiar with. And I also want to point your attention to this some kind of process parameters that you can also apply to do these predictions. And this is the one that currently opens up new avenues for us in using AI tools, because when you're considering a system's process parameters, every system is probably going to have 20, 30 different tags, and all of them cannot be analyzed individually, manually by us. So that opens up opportunities to go in there. So when you take any of these prediction tools and you get ready for it, the system will look something like this. You'll have an equipment, you'll have a sensor that goes to gateway node, cloud, and then a user dashboard. And then finally, you take a maintenance action. That based on the results coming from the portal, you take a maintenance action, right? So in some of the other presentations that you have seen, they went in detail about this whole flowchart. I'm not going to go into that, but one thing I want to highlight here is previously, when we were just doing traditional PDMs, that route-based vibration analysis, the technician or whoever is doing the maintenance, who are taking the reading, was responsible for both the prediction and the judgment. Like they would go take the reading, and then, okay, they make a call. Yes, this vibration looks too much, and then go do a maintenance. But the problem with AI tools here is it just does the prediction. It cannot currently judge based on the results. And that's where subject matter experts like us, we come in and say, okay, I made a prediction and I'm going to make a judgment of whether to act on that maintenance or not. Do I do a replacement? Do I do a repair? That judgment falls on us. And that's what I highlight here too. That separation is where I feel it sort of turns into a pitfall where a lot of these analysis tools fall into. So that's something that I want to highlight. And once this gets implemented, one of the solution looks kind of like this. And this is an example that I worked on. This is not the real data, so I'm not showing any IP. This is same algorithm that I applied on an open source data set. So what we have here is all blue curves are all past failures of the system, and the red one is the current operating condition of an asset. And then it is predicting based on the current asset's performance so far, it's probably going to fail along this line. And obviously, since we're making a prediction, any prediction comes with a confidence interval. So that's where you see this distribution there in the gray area. So based on this current equipment state so far, we have 117 cycles left. That's a remaining useful life estimation based on algorithm. And I went into in-depth analysis of this one 2 years ago at the Maintrain conference. So that presentation is available in the library for anyone to look at it as well. That's a photo of me when I was young. So, but in addition to those remaining useful life predictions, there are other algorithms too that sort of find a way into our maintenance world, and that is anomaly detection and fault diagnosis. So initial anomaly detection, that's where the other presentations talked about. It monitors the current equipment's current status and just alerts you whenever there's an anomaly. And fault diagnosis goes one level below that. It not only detects it, but also tells you what's the failure is. Is it a bearing issue? Is it a pump impeller issue? Whatever it is, it points out to a specific failure mode. I'm not going to go into the technical details of algorithms, but if anyone is interested, we can have a chat later on that. But what I want to talk today is, this is the crux of the presentation. And all these 8 steps that I've identified are some of the things that I see would definitely help you increase the ROI from these AI-based solutions that I talked about. And these are all not technical at all. You don't have to have any special knowledge. It's just our maintenance strategic plan kind of thing. And just like for the asset management plan that IAM has developed and PMAC is promoting, I also think for this new AI-based predictive maintenance solution, we need some sort of a strategy. And I don't have the full framework of that strategy yet, but these are some of the pieces that I've identified, and I'm just throwing at you all. And if any of these one solutions works for you, I think I'll consider my job done here today. So let's quickly go into these 8 steps that I'm trying to say. The first, it starts with choosing the right equipment to monitor. And we have this famous TED talk by Simon Sinek. It starts with why. And I believe when we start asking the question of why does this asset need this AI-based predictive maintenance solution, there has to be a business justification, and that considers the cost of unreliability and business criticality as well. Because most of these technology tools, it costs money. Like you mentioned, that costs money to install, costs money to maintain, and it is also an opportunity cost because you're pulling resources out of your other activities. So it has to make business case. But sometimes I've seen a couple of examples like this too. Like some assets are hard to reach. You need to have like a lot of work permit to go to a confined space, or there's a lot of it's way up in the buildings. There, yes, it makes sense to also put in those wireless sensors to monitor. It again depends on what the business goal is. If you want like a full-time visibility because the operators are working from home or working somewhere, it does make business case to install these remote sensors. So that's one. So after identifying the correct equipment, what we have to do is to also identify the failure mode that we want to target. And this I feel is the important step too, because if you look at any asset, it probably got a lot of different failure modes. And there is a term that I came across that I really like. It's called prognosability. And that tells you that some failure modes has certain mechanisms that you can predict, or that you can get alerted before a complete failure happens. And not all failure modes suit that category. And if you're trying to do this kind of predictive maintenance on those failure modes, you will not have any success towards that. So that's what I feel. You not only need to identify equipment, but also the failure mode that bothers you. And usually it will probably be the first failure mode of the equipment, because the weakest link and the first failure mode of the asset is something that reliability engineers care about. So if that's good, and if that supports you in detecting, then you're already in a great step. And if for someone using RCM analysis to drive all the maintenance actions, in the RCM, we have scheduled on-condition tasks that says, okay, if it's feasible and worthwhile, go and do it. And if some of these items say yes, this is also a good place to put in these algorithms and do maintenance. But if you're going through the RCM decision tree and say, oh, we might probably be okay with doing a time-based PM, then AI-based PDMs will be an overkill for your application. And next, when you're going with the sensors, it's also a package that consists of 3 components: the hardware, the software, and the network. And each of them has to be considered in selecting the right solution. Right now, we have market available solutions that's fully packaged, but some companies who are building this in-house need to take in these factors into consideration. And I'm not going to read this, but I want to quickly point out a few things. One is the sensor reliability itself, like your vibration sensor that are installing it. Has it been validated against a reference sensor? Are the readings correct? Can we rely on those? What if that fails? Is there a noise involved in the data coming in? That's one. And with regards to the software, the portals, they are amazing with good user experience, but it has to be able to capture feedback from the technicians so that the algorithms can automatically learn that. And this capturing feedback portion, some vendors that I've seen, they do a great job, but the other ones, it takes a lot of manual process and a time-consuming process. So there needs to be balance in evaluating that. And lastly, with the network one, there's a lot of security issues. Either you deal with the security internally within your company to allow using your network, or have all the solution as a separate network within your facility that you can operate it under as well. The presentation yesterday talked about having a mesh network. That meant there is no data loss, no data latency, Those are all great if you're trying to do real-time monitoring. So these are some of the pointers that I've listed when you're going out and evaluating, which will be a good package solution for us to implement in our facility. And once you set up all these, then the question becomes, how do we use this, right? So you have all these sensors installed, it's sending you all these alerts. Then the question becomes, what is an alert, right? And this is one of the questions that I asked at the previous presentation. And the answer was, we start with some standard alert limits, upper and lower vibration limits. And then based on feedback, we get tuned on it. So we need to define what the upper and lower limits are for your specific data stream that's coming in. And the next one is, what if the data that is coming in just spikes once above your upper limit and goes back to normal? Should we get an alert notification, or should we consider that or just a one-time event, just continue normally? So these are the questions that your platform or a solution has to address. And the next one is drift over time. This is something that I've noticed too. Like initially, when the pump is brand new, it'll have a baseline, and upper and lower limits will be based on that baseline. But over time, as the asset ages, the baseline might drift too. If you have that same limits, you're going to have lots of unnecessary notifications. So that needs to be considered too. And the next one is, who is getting the alerts once these systems are put in place? And what type of alerts are going to it? Is it just like something is spiking high, or does that information gets more, that email or text has more information? Oh, this is high. These are the possible recommendations. This is the manual that you need to go and refer to, get the spare parts, or talk to these subject matter experts. So those information should be embedded in the alert notifications. And this is something that we can borrow from big technology companies. They put so much thought into how much we are interfacing in every email, in every feed that we see, what information to package in. So that same thought process can be brought into our world to also say, oh, let's save some time in actually alerting the people the right information. And also managing these alerts. That's also a big task. Okay, if you have all these alerts coming in, how do you close it? Like what does it mean is to close an alert? Should you go and do maintenance? Should we start a work order? What does it entail? So that needs to be properly defined too. And that's the last point that I want to talk about is, what's the next step once you get an alert? Is just a manual inspection, or is it automatic work order triggering? Or should you ask the operators to stop operation? That needs to be properly defined there. And that takes me to the next pointer that I want to talk about is streamlining all the support systems that you have, in addition to having just that AI-based predictive maintenance solution. And this is a simple PF curve. Most of you might be familiar with. We have equipment health, and it gradually drops. Usually it's not this smooth curve, it's all ziggy-zaggy, but just for a presentation, your equipment starts failure here, and then it goes down. So we have this time interval for us to react to it, right? So in that time, you need to have the personnel who's available to do repair. You need to do the right diagnosis. You need to have the spares in time, and also whatever the operations or anyone is responsible for it has to approve you to go and do the maintenance stuff. So that's a lot of time already taken out from your time interval. You're losing this huge chunk of time from actually doing the maintenance work. So your range time reduces. But what if we stack up all this together? So right from the moment you get an alert that there is some anomalous behavior is going on in it, you can save all this time. And for the same asset, you can see the difference between your net PF interval, like how much time you can save just by streamlining all your support services. And how can we do that is all these personnel available, the onus falls into planning and scheduling work to have the right number of people at the right location. And if there is a fleet, and dispatching the technician out in the fleet, the time taken to travel to the site, those are all included there. And then the right diagnosis, having all the manuals, and the spares too. This also supports that, having the right spares for your equipment. And finally, finding some support with your operations team so that all of these are fully streamlined to support that you have the maximum time to do your maintenance work. And then it comes down to, okay, all the time savings is great, but only if the algorithm that you're relying on to make a prediction is accurate enough or it's good enough, right? So if you take any algorithm, it can give you alerts, can give you an alert that's actually good, and it can give you some false alerts too. So these are all the four possible combinations of all that can happen. And what I am trying to point out here is, you need, as maintenance engineers, we can find a way to evaluate the algorithm's accuracy, how accurate it is in detecting the actual failure when it's there. And we can rely on two performance metrics. One is precision, and another one is recall. So these two are the terms that I borrowed from machine learning community. So anyone who's involved in writing algorithms, they are familiar with this precision and recall terms. So precision is a measure of it's a measure of the number of actual failures to the all predicted failures. So that's this one here. And then recall tells you it's a measure of count of actual failures, count of predicted failures to actual failures. And that's maintenance time to the false negatives here. And it's not like we can pick and choose which performance metric to evaluate on. We can rely on both, because if you have a low precision and high recall, you will have a high cost of missed failure. And similarly, on the other combination is cost of incorrect detection. So I added some examples here. If you look at on the y-axis, we have wind turbines. Wind turbines, okay, yes. The inspection cost is minimal when you compare with the actual cost of a failure. You can have all these. But when there is a false alarm, the technician has to go there, shut down, climb up the ladder, go inspect it. And that's a lot of time wasted there. A lot of resources too. So that means the cost of an incorrect detection for that particular application is too high. So you can sacrifice something and take a little bit more on. We can go with low recall and go with high precision for those kind of applications. But for other applications, one example is pharmaceutical fermenters, where if something goes wrong, the whole batch is wasted. There's a high cost of a failure there. Here, we cannot miss detecting any failure. We need to know everything that's happening there. So these are the two kind of like levers that you can tweak to tune your algorithm so that we can get some balance in the middle. And you don't need to know all these metrics. What I'm trying to show you is, okay, when you are getting it down this path, if you're talking to some vendors and they're sharing you some of this information, you can ask this question. So what's this algorithm's accuracy? What does its precision say? What are its recall values? So that's one way to do that. And it's also not a standard process. There's going to be a lot of iterations going back and forth, because once you deploy some sort of an algorithm, you're going to monitor it in period to see what's the performance has been. And then you can then evaluate, is this good, or should we change any of the performance metrics that we are using it to monitor there. So all this requires a little bit of training to the end users. And that's the thing, that's my 7th pointer that I've said here, is the end users who are actually using these portals needs to be aware of some basic information on what these different metrics are, what they're doing, and what does it actually help, how does it actually help us in getting the job done. And this is where getting the buy-in from them, having them involved early on in the process, and making the whole process tailored for them really helps. And the last thing I want to highlight here is developing some procedures for the whole organization so that once one person is trained, they can pass on the training to other people as well. So that standardization goes in when you are especially scaling up. And there is a term here, it's the pilot purgatory, because we do projects, we pilot it, and then it dies off. Because scaling up is these kind of AI solutions, it's a different beast. And I think that's because when there is all the steps that I mentioned, imagine doing it for 100, 150 of these assets. You need a dedicated project team. And in one of the articles I read somewhere, there's going to be a future job title that's called Predictive Maintenance Specialist. And their job will be just to maintain these algorithms. Okay, how are they doing? How can we tune these algorithms to make it give better results? So that's dedicated project team. Do we have resources to form a team and manage that? That's the question we need to answer. And standard and data policies too. Like what type of data that you're capturing, and how are we even tagging the data? In a couple of sessions, we talked about data labeling. So for every asset, just like right now we have a syntax in your CMMS recipe that, okay, we're going to capture, make, model, the sizes and everything. So like that, for going with this AI-based solutions, what type of sensor information that we need to capture? So that needs to be standardized across the whole organization. And it also helps either if you have a hub and spoke model or a point-to-point model in sharing the data. Because I've seen in companies where they have a centralized digital team and then they implement solutions at various sites. So that's top-down, pushing it down. But also the other way is, okay, we have a localized system that build their AI solutions individually, but how do we scale it? How do we share that information across multiple sites? Because getting assets, getting trained on the assets is very expensive affair. And if you have similar sites, you can take on the learnings from one site and pass it on to the other one too. So that's the 8 different steps. And all of that finally comes into this idea that I've called double umbrella model. That's, if you take a reliability team goals, we have a business goal on the top, and then the reliability program, and then reliability AI projects. Similarly, if your organization has some other AI work that you're planning to do, it might be for a marketing team, or can be a finance, or just manual LLM work for service orders. Those should also be factored in, and we have this kind of a double layer here, where your organizational AI policies should match with reliability team's AI policies. So if all of these 8 steps are put together in a series pattern, we get this equation. And just like a reliability block diagram model, if any one of them gets improved, your overall reliability gets improved. And that's the thing that I want to complete the talk today. And this is the takeaway slide. So I've summarized everything here. If I know initially we talked about low ROI. If any of these 8 steps is if you can find a way to improve or increase its effectiveness, then you are in the right strategy to get more value out of these AI-based solutions. Thank you very much, everyone, and I'll be happy to answer any questions.
Does anyone have any questions? If you do, I'll give you the mic. That way it gets recorded.
No, thanks, Arun, first of all, for your presentation. It makes a lot of sense. So I was in my one part of my career where we were subject matter expert on some of the stuff, and we had plant information system pulling the data. And the expectation was to set the upper and lower boundary. It's not that easy as it sounds on a screen. We ran into a lot of trouble. We constantly were bombarded with a lot of alerts coming in, to a point we couldn't do our job and just were mitigating all the alerts all day.
Yes.
Till we came to a point where we had to really turn it off.
Yeah.
So yeah, it makes sense. That was our OpEx on that one.
Mm-hmm. Yeah, I can respond to that comment in just defining the upper and lower limits. And right now, if your system is dynamic, if it changes its operating conditions, then it becomes even more difficult to set those upper and lower limits too. And that's where I feel when you combine not only the condition data, like vibration that's coming out, all the operating data that you can feed into, and everything is a multidimensional representation of the same operating model, these assets. And that will give you like a picture. Okay, if the RPM increases, then I know that I'm in a different operating mode. The upper and lower limits change, the alarms change. So the algorithm has to be smart enough to recognize that. And at least us, like end users, we have to be smart enough to tell the builders or developers saying, our operating mode is going to change month to month or year by year. Capture all this together.
Yeah, no worries. So what we ran into issue is, one is your operating envelope, right? We allow folks to operate in that envelope. Then we have a design operating envelope that we allow as an engineering to maintain. So this is what you're going to go. And you got safe operating envelope, which the ops wants. We could never agree on a common operating envelope.
Yeah.
We spent like 2 years almost debating it. What is the limits? Everywhere, by design basis, we need to ensure that everybody has a defined operating envelope. And there is a reason why we have that.
Yeah.
So that's one of the big issues that we ran into. So all that is awesome. But all those intricacies need to be sorted out between multiple stakeholders upfront.
Yes.
Otherwise, it doesn't go anywhere. Right?
Correct. Yeah. I agree.
Thanks. Thank you.
Thank you for the presentation. Very insightful. The question that I have, referring to your double umbrella slide, you referred to data policies. It sounds like a very precise question, but I find it is key to unraveling all of the investment. For example, we've made a lot of investments in real-time asset monitoring onboard vessels, so moving plants.
Yeah.
And we're falling over ourselves now because we never started with any data governance.
Yeah.
We didn't even understand that as a concept, but 4 years later, we're realizing it's an issue. So my question is, who owns data governance? Do you have any recommendations? Because I don't know if it's the technical team, reliability team, the legal department, the finance department.
Yeah. The answer to that question is, I don't know for that. That's where I believe I just made this abstract thing here, because I feel it should be decided within the organization. And I also don't believe that the thing that you might choose will not work for this person too. Right now, most of the things that I've seen is we do implementation within maintenance team, within a reliability team, and then they own the data. I mean, they are at least responsible for managing that. But if you're scaling up, there may be like a site-wide. But if it makes economic sense, you talked about the computing cost too. If you're bringing everything internally, then the whole organization-wide operations team can own the space in the internal cloud that you have and have all those data governed. And the data might be there, but then the question now also becomes the algorithms that you're building on top of the data, like who owns that? Because different, like this person was pointing out, different teams can give in more inputs and change these parameters. Like operations might push into change algorithms so that I don't get alerts. Maintenance might say, oh, I need these alerts. So now you're constantly tuning these algorithms, and who's the final responsible person? So that's where I believe there should be a champion, kind of like a change agent who's responsible. Okay, all these changes and everyone goes through this person and they manage it. Maybe a change implementation process, but I have not come across that problem. But I'll be curious to hear sometime down the road like how you tackle that.